connection, but now he's okay.
Yeah.
So while I read, I let Professor Wang to prepare maybe 1 minute. I'll give a quick introduction and then I'll give the floor to you, Professor Wang.
Yeah. Okay.
Okay. This is the our plenary lecture 2 by Professor Luju Wang from Shanghai Jiatong University, and his work is on he'll talk about a research outlook on energy, water, air nexus, which is coincide with the Thai festival. Now we have today is our 14th Lantern Festival or Loi Katong, which is when we pay respect to the goddess of water.
Energy, water, and the nexus. Just a moment. Okay, I find.
And Professor Wang, if you're ready, yeah.
Yeah, I think I have a. I need to open another file. It's another,
okay.
another file.
Professor Wang is Professor Wang have written over 10 books and more than 600 papers. He's very well known and many awards from domestic China and many awards from international. So, and he's working very hard in research area, helping with young people get published. He's an editor of Energy Journal, Elsewhere Energy, and also the editor of International Journal of Refrigeration. And I asked on behalf of the organizing committee, I wish to thank him for his generous time giving, and then he can spend some time with us here today.
Okay, I am ready. I think just a moment.
Okay, yes, the floor is yours, Professor Wang. You can share the file.
Yeah. So you could see that, or?
Yes, the file see okay. Can I just have a quick reminder to you, please, Professor Wang? Our next session will start at 10 o'clock. So we have about 30 to 35 minutes.
Yeah, okay, so I will go quickly.
Thank you very much.
Yeah, so this is work actually I named Adsorbent for energy conversion and management, and it's a cross to energy, water, and the nexus. So I started from adsorbent research. So this is an introduction. So it's a big picture for sustainable development because it's energy, water, and air. It's related, and in this case, I had a lot of researches with adsorption and adsorbate. So different kind of adsorption, refrigeration cycles, and also it's cross to energy, water, and air nexus. So a brief introduction for the adsorption. It's a adsorbent, it's a porous material, and it's decided to the pore size from micropore to macropores. When it's a micropores, even very less pressure, you will get the adsorption process to get the moisture that's condensed. But if we increase, so and then so it's just a pore filling for in this kind of micropores, and this just shows how much is filled depending on the micropore volume. So just you get a condensation of moisture to liquid. And if we just increase the size to the mesopores, so maybe we have single layer or double or multi-layer for the adsorption process. But if you still increase the pressure, then you get more. So it's a more from mono-layer to multi-layer adsorption process. So it goes, when the pressure goes higher, you get the more adsorption. And this is also related with surface area. So it's especially for the adsorbent, that porous materials. So surface area plays a very important role. And also the surface, whether it's a hydrophilic or hydrophobic. And if we will still increase the pores to the macropores, then pressure goes higher, and then you could get capillary condensation. So at last, it's filled with all the liquid. So this just shows we may have some kind of jump. So because at first it's a small mono layer or double layer, but suddenly it's pressure goes higher and you get this kind of jump. So this is for the capillary condensation. So this is important for the adsorbent. Some kind of adsorbent that if it only have a pressure difference very small, you could get a very big difference for the adsorption. So this is why that for currently for the MOF material, it's so important for this kind of process. And then from the International Union of Adsorption Society, they have already have these kind of figures just to show different mechanism. But for MOF material for small size and the medium size, the MOF material, especially for the massive pores, so it's from about 3 nanometers. So now it's a very, very hot topic for researchers. It's has a very high jump of adsorption process. And if the come to the micropores, it's silica gear, and then it's a general actually. So original adsorption is small, but when it's saturated, so nearly 100% of water for the relative humidity, then you get the capillary condensation. So for the adsorbents, actually we have porous adsorption with a micropore filling or capillary condensation. But now we also have no porous adsorption. It's a kind of so-called mobile adsorbent, especially this kind of adsorbent like a so-called hydrogel. So actually you need to create some adsorption points and then to gate adsorption. And then hydrogel could extend its abstraction of water liquid. So then this kind of adsorption could be very huge. And also we could have a composite adsorption to use a combination of so physical adsorption and liquid, so chemical absorption. So in this case, this could try to increase the adsorption by this kind of liquid because it has function of solid absorption and then liquefaction and then strong liquid. And then like a lithium chloride could absorb more water and then to the weak liquid. So in this case, you enlarge the concentration changes for the adsorption. And also there are some ASEP adsorbent very similar to the MOF materials. So like this kind of farm materials. And but usually this jump is only about 0.3 or 0.2. But for MOF, you could have a adsorption jump maybe about 1. That's very huge. So this is for the MOF material. So there are a lot of researchers in recent years, and so it's a very hot topic for material scientists. And now it's also transferred to the applications that try to use this kind of soup adsorbent for some kind of research, especially for this MOF material. So you could see the jump with a very small relative pressure or relative humidity changes, you get a big jump, more than 1 gram per gram adsorbent. This is for the adsorption of moisture water from the air. And also there are some more development for the MOFs and also some researches for some analysis theoretically for its performance. And now we also developed the composites, so-called that confined to in a porous matrix, because that like lithium chloride or calcium chloride have a very big absorption capacity of moisture from strong liquid to weak liquid. But it may have the problem of leachables. So in this case, it will be good to put this that into the micropores of porous material. In this case, the liquid will be self-sustained inside this porous medium. So in this case, our last colleague is Aristotle. So he suggested a selective water adsorbent. So this just shows that for the development of composite adsorbent, so we have porous matrix and the lithium chloride, and then if it's combined, and then we did a lot of researches for different kind of, and we find that a silica gel B and C is usually for 4 to 10 nanometers. That's very good to sustain lithium chloride or calcium chloride into the micropores of the silica gel. And this is just a taste, and this is normal silica gel for the adsorption of water. But if we're using composite, so it's enlarged very huge. And also this could be, we could using some process to just prevent carryover problem of liquid, the leachages, to get the liquid, so to keep it inside. So this could be controlled by a thermal process. So this just shows surface morphology actually for different kind of adsorbent. So when it's enlarged in the microscopic, and to see even using some activated carbon fiber with lithium chloride. And this just shows that the figures just show. Okay, I'm sorry. So, and also we did the research with morph materials that try to get the lithium chloride comes into combination with morph materials. So in this case, if it's a morph material adsorption, and now we could get the adsorption of water like this. So this is just this line just for pure lithium chloride, but this is pure for morph material. Now we go between, but try to use a morph material to install sustain lithium chloride inside. So in this case, what we found that for the adsorption and the desorption process, so it has a very enlarged performance. So this paper was published in Advanced Chemie International Edition. So this is a new phenomenon, and we concluded that a variety of solvent could be considered. And so there are a lot of options. So most options are here, but now morph comes here. So usually, so in this case, if you find some suitable applications, so we could try to apply morph materials. But currently, the problem is morph material is still very expensive. And another thing that is for the hydrogels and used for the sorption process, and then if you have some micro points just adsorb moisture, for example, with some lithium chloride, for example, then you will get adsorption, but this space will be very good hydrogel, will expand, and the water will be reacted with polymer to have a long chain, and in this case, it lasted here. So, but if you just added a little bit of temperature to 45 degrees, for example, saying water, so it changes from hydrophobic to hydrophilic. Actually, in this case, liquid could be separated very easily. So in this case, this creates another application that why with the hydrogel could be used to handling that the atmospheric water adsorption and for the atmospheric water harvesting. So also we did this kind of work with hydrogel water adsorption, and so 1 gram of hydrogel could get about 6 grams of water from the atmospheric air. So in this case, it's very good to be considered to be used in dry area. It's especially in some arid regions, desert area. So this is the real test, and this was published in ASEP Materials later. This is just to show in the night we get adsorption water here, but during the day with the sunshine you get the release and you generate water for drinking. So after this kind of material research, we need to the component and to the equipment. So in this case, you need to design a lot of adsorbent bait, possibly packed bait, and integrated with heat exchangers, and you consider how to generate for heating of the adsorbent, and also how to cooling down of the adsorbent. So when it's heated, you get a regeneration, so the absorption of refrigerant. When it's cooling down, then you have the refrigeration, evaporation, adsorption process. So this just shows if you have a thermal siphon and to use a boiler here for heating and the cooler here for cooling. So then you could very easily, no pumping is needed. So this was our design for the adsorption system. And also we developed some desiccant coated heat exchangers. So there's a heat exchanger coated with desiccant materials, even morph materials. So this work was done by the Germany colleagues. They are using morph material coated there. And we coated desiccant with silica gel and composite lithium chloride. So this composite that's used. Why we do this? So to compare with the silica gel with this composite, so it's a very linearly. And so if we have relative humidity changes from 30% to 80%, then what you could see that W value could be increased just 100% increased or even more. So the sorbent only about 0.25 millimeter thickness. And what's important that we try to use this for temperature and humidity independent control system, because for air conditioning, you have liquid desiccant and with the sensible heat exchangers, dehumidification and cooling, or using desiccant luter dehumidification and the sensible heat exchanger for cooling. In this case, normal evaporation air conditioning system, you could get the evaporation temperature more than 15 degrees centigrade, because dehumidification is done by the liquid desiccant or solid. But now we get this kind of desiccant coated on the heat exchanger. So this will be a water absorbing heat exchanger. So this was developed first by Shanghai Jiaotong, and then we did some research. And this just shows for desiccant heat exchanger in the air duct. So we have heating and cooling, and normally have about a 30 degrees temperature difference. So cooling could be about 15 degrees and heating at about 45 degrees. So this just shows and the original heat exchangers, and then we coat it with desiccant and doing the test. So this just shows also the measured data. We had to have a dimensionless analysis because there are too many specific data, but at the last so we treated only 4 this kind of integrated parameter. So this we using 4 dimensionless index and obtaining a graphic general solution. And also we made a compilation with a micro channel heat exchanger or thin tube heat exchangers. So micro channel heat exchanger could be much better than thin tube heat exchangers. And also we get the analysis, the measurement data for the Nusselt number and the Shilton number for the heat transfer and also handling of latent heat for the humidification. So with this system, and we could develop a variety of adsorption systems. This just shows that for heat pump applications, that usually we need 2 adsorption, 2 adsorbers to get continuous operation, just to shift the phase of the both adsorption. So in this case, we could introduce heat transfer fluid for the heat recovery when one finished. So generation, one finished adsorption. So the high generation temperature at a high temperature could be used to generate another adsorber. So you need the heat transfer fluid for the heat recovery. And this is the normal design that for the sorption system with adsorber, and this is cooling, and you get evaporation, then you get output of refrigeration. But if we heat it, you get the regeneration. So you will get condensation, and then liquid come to the receiver. So this is just very simple for the adsorption bait. But now we also developed for the 2 bait, so not only heat recovery. So I proposed the solution, the mass recovery, because when one adsorber at high temperature, high pressure, and another adsorption at evaporation pressure, you still have pressure difference. So in this case, I could propose to use the pressure difference. So this paper was published in International Journal of Refrigeration. That's 20 years ago, but it was the first to demonstrate how mass recovery could work. So this just shows that Google changed the process. we just open the valve of tube bed, and then you get the vapor recovery to the just a medium pressure. So you get more desorption or more adsorption. So in this case, you could increase COP. Could be possible for 100% increase. So it's very simple. And then we developed this commercialized product from 10 kilowatt to 50 kilowatt. Adsorption chillers usually need about 60 to 85 degrees hot water to power. And this just shows this is the evaporator. Actually, that's a adsorber, condenser, receiver. But here is the evaporator. So actually, when this adsorber is cooled down, you get the evaporation here. So in this case, the cooling could be output to this thermosiping. So you get 15 degrees in and you get 10 degrees out. So in this case, when this is heated, so there is no heat transfer here because it's this is a very low pressure. That's because it is on the water. So then you will get a heat transfer here to get the cooling output. So this is the design. And now the commercialized product of adsorption chillers. So now they all use my mass recovery cycles. So it's used for all commercial products. And now I'm proposing this kind of system could be possible to using about 60 degree hot water to power adsorption chiller to get about 20 degrees chiller with a COP 0.35. So this could be used for the data center because now it's a water cooled, and usually originally it comes to hot water, so it comes to the cooling water power. Now it comes to the adsorption chiller. So we made it a test and powered with about 50 degree to 60 degree hot water, and this just to show the COP values. And we get the cooling water about 20, about 20 to 24 degrees centigrade. So for a supercomputer, usually if it has a 400 kilowatt waste heat, it could produce 150 kilowatt cooling power. So in this case, could save about 40 to 50 kilowatt electricity. So this is used for the electrical powered chiller actually. So in this case, so we made this kind of balance and find that this kind of design is reasonable. And now we are pushing the project to collaboration with Huawei for the data center. And also we did some other work for data center for the so-called thermal sorption thermal battery, and try to get 2 adsorbers when it's generated. So, and then separate it and then keep it. But when you need the cooling and you just open the valve and then, so suddenly you could output the evaporation to get the cooling. So this is a kind of adsorption cold storage. And this is on the request of Huawei, and we developed such kind of system. So this is the first model for about 15 kilowatt and to sustain about more than 15 minutes. So now they want us to build a 150 kilowatt. So now this is on the way of design. So it's a very compact system, but this is used for certainly for data center if electricity is shut down. Originally, they need a big backup for the electric battery. So in this case, they consider to use this kind of thermal battery for this kind of as a backup for cooling. And also now for the heat pump, there are all other kind of researchers try to replace the normal air conditioning system with evaporation temperature 15 degrees centigrade, condensing temperature to use 45, because originally 7 degrees and 54. This is Chinese standard. And you need 7 degrees for dehumidification, but now we use evaporation temperature 15, but dehumidification by the solid desiccant. And the condensing temperature reduced down because the solid desiccant heat exchanger originally used as evaporate. It's stored with adsorbent water moisture. So you need the evaporation for the desorption. So in this case, it's like a evaporative condenser. So in this case, what we got, so the COP value could be increased 100% for the theoretically in this case, because the humidification normally that's about more than 40% is used for the energy for the humidification. Now we just use actually, so this just to show the air handling unit, and the system only one compressor and two heat exchangers, but evaporator and condenser need to shift the phase. So maybe every 5 minutes you need to change the heat exchanger from evaporator to condenser. And also we have four-way valves here to make the shift of the phases of the heat exchanger, and also air duct. You need the pump by the fan. So in this case, what we got, the cooling model, the COP system level, that's about 6.2. So in this case, 1.5 horsepower compressor, you could generate about 7 kilowatt cooling. So this is a very good research work. And now we are pushing the uses for efficient heat pump for train vehicles. So already, so we transferred this kind of patent and to manufacture of this kind of train vehicle air conditioning. And we use originally the one chamber with a two roof and air conditioner. So we just using the same size and then put our concept, and now already that's built in the industry. And so the COP original 2, now we need to increase to about 4. Target is 4, but we try to increase to 5. So this is our research. And also we developed some other works. So for energy storage, for example, so this is for heating and using the thermal battery. So with electric heating, you get a regeneration and you get a weighted hot air for heating. But and then energy is stored from heating to adsorption potential. So when you need heating again, and then, so this adsorbent bait, so when you get the room air comes here, and it will be heated again. So you need in the night, maybe heating with electrical in the day, heating by adsorption. So in this case, create a new model, but that's more important is that if we develop this model to warm, dry air at about 40 degrees centigrade or 35 degrees more, so it's good for heating. So we did some research tests about this work and also generated a model, so-called a thermal wave reaction model like this. So what we found, it had a wavelength, and also we have a velocity for the move of the wave, and so the design of that's a length of this kind of bait. So in this case, if we set about 5 hours or 8 hours, so then you could make, so you see that the temperature output goes up and then it will be stable. So this time is needed for our design. So relative with the length of the adsorption bait. And then after that, it will go down. So in this case, we need the output for the stable temperature. So this is for chemical thermal battery. It's very important because originally all researchers just at first, the very high density, high temperature, and then drop it down very quickly. So what we need is to get a stable output. So this is our model developed. And also other works with the AWH, so-called I published one paper in JOR for the progress and expectations of atmospheric water harvesting. And also we developed some, it's just simulations and in the data areas, because we considered to using this kind of composite material could be very good and applied all the world, whether it's in dry or in humidity regions. And this just shows the real operation, and we developed 50 liters of water per day by solar energy, actually. So this developed, so at a humidity about 70%, but when we tested at a relative humidity about 35%, and in winter time, so then it's about 18 liters. So in this case, we considered it could be universal scalable sorption-based atmospheric water harvesting by this kind of devices. And for this kind of what harvesting, I made a paper just this year. So a perspective for the adsorption-based atmospheric water harvesting. So I try to classify everything and say what will be the future for the development from materials to components and to larger scale applications. And I think very recently, Science and Nature, just in November, published 2 papers. So to say the feasibility of atmospheric water harvesting. So another is that's in Nature. Another one in Science for the structure of morph material and its capability. So that means this kind of area could be a very, very interesting area. So the both big journals they did. And then Nature is also a big journal, currently with the impact factor more than 40. And also in Jaw, we published several papers. So this is for the localized humidity control with a solid state humidity pump using, actually I'm using thermoelectrical system. And so try to pump moisture from low humidity environment to high humidity environment. So that's similar for heat pump from low temperature heating to high temperature output. So I
am sorry to interrupt, Professor Wang. I would like to ask you to conclude maybe in a few minutes so that we have maybe discussion and then for the next session, please.
Yes. Okay. So
thank you.
And we did also more for the applications in the buildings for the humidification with solar, and did a test. And very recently, so also one paper in Jaw and for the thermal management using for the electronic based cooling. So with sorption, so when it's in high temperature, when the high heavily load, then temperature goes up, but it will get the regeneration of moisture. So it will restrict the cooling. So this is a test we only using less than 1 gram of morph materials. But you see that we get the temperature down for more than 8 degrees centigrade, and then we consider for the usage with the mobile phone. And now already developed this for the mobile phone cooling, and the student did a lot of tests with the games, and then to verify that how the performance that increased about more than 20%. So it's very simple, just to use 1.7 gram of the kind of morph materials. And so there are more, and just also for the greenhouse, because it's we need to make a recovery of the moisture water from the greenhouse, and so this water could be generated with solar and then received in the tank, and then could be used for irrigation again for the agriculture. So this just shows other work, and also I think for this kind of materials, so whether silica gel or morph or composite and the hydrogels, so they are all very important, and they could find their applications in different areas. So I think a future application could be adsorption heat pump, some battery, AWH, and desalination, and some management. So in this case, the need of the collaboration of material science and also applied scientists. So I collaborated with some Russia, Japanese colleagues. So we have a review paper, so called Bridging Thermal Management and Material Science in nano energy, especially considering of the morph applications. So, and a lot of contribution from my PhD students. So thank you very much. Thank you.
Thank you, Professor Wang. I'm sorry for rushing you, but okay. For the next, we will have a next session at 10 o'clock. But we still have something like a few minutes for discussion. Is there any question from the floor, please? Professor Philos Alam, please. You have to open your mic, please. Speak. Yes.
Yes. Thank you, Professor Zhejiang. It's a beautiful presentation, and also it encompasses many things. And we are very pleased to see that some of your work already has been in implementation in the commercial application.
Yes.
I just wanted to ask you a very simple clarification that you said that your system is now being used in the HVAC system in the train. So what is the energy efficiency using with your system compared to the previous existing system?
Yeah,
Thank you.
The original one, actually for air conditioning, that's a standard is COP about 2. And now we get about a 3.5, but we will reach 4, I think. So in this case, a very good opportunity that one company from Germany, that joint venture in China, and a German company have 51%. So now we transfer this technology to them, and this company have about a 25% Chinese market. So we could use for the metrons, and what's important, I wanted to extend it to Chinese high-speed train.
Thank you very much.
Heating and cooling. Yeah.
Thank you.
I think we could have one more question before we go to the next session.
I have.
Professor Somnath, please go ahead.
Yes, but in high-speed trains and all those part of it, it is a really expanding thing for China. Unbelievable speed. So what do you think that the implementation of these technologies in the high-speed trains of the other countries?
So actually, in the high-speed train in China at the moment, cooling is by air conditioning, heating is by electrical heating. So in this case, what's important that change it into the heat pump. And also in China, you know, Chinese high-speed train from North China to South China. So maybe in 5 or 6 hours, that's 4 seasons. It have 4 seasons. So in this case, heat pump could be a very good opportunity. And also it will be depending on the Chinese strategy and collaborations with foreign countries. And now you know that the Chinese promoting the Chinese high-speed train to Thailand, and also Pakistan, and hope to India. So I think now we have the most commercially that's about 350 kilometers, and now I think maybe next year it could be about 400. Yeah, some lines. So it's a really very good opportunity.
Yes, yes. Thank you very much.
Yeah.
Okay, thank you very much. I'm sure that there are a lot more interest who wish to ask or discuss about the topic with Professor Ruju Wang. I'm sure he will be happy to answer your question. You may contact him via the email and the resume that we put on our website. For now, we wish to thank Professor Ruju Wang for entertaining us with this wonderful topic of energy, water, and air. Thank you very much.
Thank you very much.
And can we, everyone, give a round of applause to Professor Wang, please?
Yeah, thank you.
And I think I have to stop here because we have one or 2 minutes to switch over to the next session. Thank you, everyone, for their participation.